you for the nice introduction and also to Bermudian for organizing this nice symposium. So this is joint work with Ashraf, who is a student from Sorbonne University in France, and Hannes Clement from Wuppertal University. This is still an ongoing work, so if you have any comments or suggestions, I would really appreciate it. So I will be talking about Port Hamiltonian systems, and I need to give you a small motivation why I have been working, and other people have been working on these types of systems in the past years. So Port Hamiltonian systems are energy-based systems. So the language they speak is energy, basically. So they are great for multi-physics modeling. So if you have, like, for example, I will give some examples later, but if you have, for example, like an electrical network combined with like a gas network, and then you want to have a model of the whole thing, you can model each one with energy and then combine them in an easy way between quotations. So the good thing about them is the interconnection. So interconnecting a Port Hamiltonian system with another Port Hamiltonian system gives you another, again, like a general Port Hamiltonian system, and then you basically preserve the properties that you had of the individual systems. Also, the internal components of these Port Hamiltonian systems have a physical meaning. So we don't have like a general matrices that represent the system, but each matrix has actually a physical meaning behind it. And finally, they have nice properties. The two most important ones are passivity and stability. So if you have a Port Hamiltonian system, you are guaranteed to have stability and passivity. Let me go a bit into more details. So consider a dynamical system with inputs U and outputs Y. Then we can represent it as a nonlinear Port Hamiltonian system in this way. So here we have the outputs Y and the inputs U, and then we have states X. And then one important characteristic of these models is the Hamiltonian here, that you may also know from physics. So this is basically the generalization of the Hamiltonian systems. And then to say that this is a Port Hamiltonian system, I need to satisfy these properties of these matrices. And then each of these matrices has actually a physical meaning. So as I said, H is the Hamiltonian, so it represents the internal energy of the system. J represents the internal structure, how the energy flows between the different states. R is the dissipation in the system, or the loss. Then F and P are the port matrices. So these are the matrices that communicate with the external world in a way, with the inputs U and the outputs Y. And then we have the feed-through term, which goes directly from the inputs to the outputs. Okay, so if we satisfy these conditions, so J is Q-symmetric, R symmetric, positive definite, where you can see it here, and K is positive semi-definite, then we can say that our system is Port Hamiltonian system. And then we have some nice properties that I will describe in more detail. Okay. To make things simple and more understandable, let me now present the properties in the linear case, but you can do the same thing for the nonlinear case. So consider a linear system, A, B, C, D, and then we can also write the transfer function using the Laplace transform that describes the relation between the inputs and the outputs in this way. Then if we are in the linear case, then we can write our Hamiltonian as the quadratic function in terms of Q. And then I can rewrite my nonlinear Port Hamiltonian system in this linear fashion, where now J minus RQ is basically my, it's basically my A matrix. And then F minus P is the B matrix, F plus P transpose Q is the C matrix, and so on. And then I have also the usual conditions, and then we can say that this is a linear Port Hamiltonian system, and then we can see the relation to the standard linear systems. The difference is that now I have a physical meaning for every matrix here in this model. So J, as I said, this represents the internal structure, R is the dissipation, and so on. Okay, so now let's look at the properties. So actually this Hamiltonian function that I talked about satisfies the dissipation inequality. What is the dissipation inequality? Consider the definition of passivity. So a system is passive if it basically satisfies this dissipation inequality with some storage function S. And actually our Hamiltonian satisfies this dissipation inequality, and then we know that directly that our system is passive. Passive, for those who are not very familiar with the concept, it means that the system does not generate energy internally. This Hamiltonian is also a Lyapunov function, so it satisfies the Lyapunov inequality, which means that the enforced system is also stable. So just from the structure, we have passivity and stability. One other formulation of passivity, and a bit easier one to verify, is this using this Kalman-Yakovlevich-Popov inequality. So we can say that the system is passive if we find a solution Q that is positive semi-definite that satisfies this linear matrix inequality. So given an ABCD system, if we find a solution Q, we can say that that system is actually passive. If D plus D Hermitian or transpose in the linear in the real case is invertible, then we can take the Schur complement and then we can write it as a linear, as a Riccati inequality. Why this is important? Because if I'm given an ABCD system and then I find a solution Q to that system, then I can rewrite my system as a Port Hamiltonian system in this way. So we have my A, B, C, and D, and the solution of the KYPQ, and then I can rewrite the system in a PH way with the matrices J, R, and so on. So now we have a way to write any system that is stable and passive in this Port Hamiltonian way, at least for the linear case. One also other property is positive realness of transfer functions. This is not really relevant for what follows, so I'll just go through here quickly. But basically, the main property that has to be satisfied is that this Popov function has to be positive semi-definite. And so basically, this is like a diagram that summarizes these properties. If I have a Port Hamiltonian system, then I have all the other properties. So KYP is satisfied, I have passivity, the system, the transfer function is positive real, and so on. Be careful, the inverse relation is not directly satisfied. We need some extra conditions. If you're interested in the details, you can look at our paper where we look at this also with the algebraic constraints. So if you, in addition to your differential equation, you have some algebraic constraints, then you are in the DAE setting, or also called sometimes descriptor system. Okay. So now we have all this theory that we can use to model multiphysics system. This is just one example. So this is a power to gas system. So we have on one side our power system, on the other side our gas system, and there is this power to gas unit that transforms basically the power to gas. And then if we wanted to try to model this in the traditional way, it would be very difficult because the variables or the units don't really match. But if we do it in a Port Hamiltonian system way, then we can use energy, which is a common quantity between these two kinds of systems. So we can model this alone, and then we can model this alone, and then interconnect them. And then the resulting system is again Port Hamiltonian. And this was done in this paper. You can have a look at it if you want more details. Okay, so we have all this theory that we can use to model this kind of systems. So why are we interested in data-driven modeling now? So I will motivate it with two projects that we have been working on. So the first one is digital twins of electrical machines. So we constructed models for these kind of machines, but still there are some phenomena that are not really well understood. So one of the functions of the digital twin is to do monitoring. And one of the main causes of breakdowns in this kind of motors is the insulation. So over time, there is this problem of partial discharge. So there is a very small leakage of current through the insulation of the system, and this may cause short circuits and then the breakdown of the machine. And this is, of course, we don't want to do it. We want to predict it in advance. But the problem is that this partial discharge phenomenon is not very well understood. So we don't really have models for this. So people, what they are doing right now is to actually stop the machine and do some tests. But this, we don't know. We want the machine to run as often as possible, let's say. So one way to do it is through data-driven modeling. If you are more interested about this application, you can have a look at our archive here. The second example or project that we worked on is modeling gas networks. So trying to have a global model of the gas network of Germany in this case. So we were able to model using Port Hamiltonian systems most of the components, transmission, gas flow, gas generation, and so on. But one problem remains is the compressor station. So in the overall network, the compressor station, its role is to change the pressure from one level to another. That's all it does, but it's a very complicated, it's a whole building, as you can see here. It's very complicated, a lot of control systems inside. And actually, engineers, what they do is they follow this kind of curves and with some operating points, so it's very heuristic. But what we want to do is to actually model the compressor station so we can interconnect it with the other components and have another overall system. But it's so complicated that we cannot do it with the traditional way, so we have basically to use data-driven modeling, and we have a lot of data for this compressor station. We have data for like 3 years that we can use. Okay, so let's first look at what we already have in the literature for data-driven modeling of these Port Hamiltonian systems. So first of all, if you are given only input and output data, so what you could do is do like a standard realization and then do some optimization. This was done in these two papers. The second one is to do some parameterization of these matrices because they have a special structure, and then again use optimization. The third method is to solve the LMI. So I told you earlier, if I have a solution Q to the LMI, then I can have a Port Hamiltonian representation, but this is very limited because we can only solve for very small linear matrix inequalities. I think the maximum realistic or dimension is like 10, which is not very useful, I think, for our applications. And then if you are, in addition, given state data, then you can do PHDMD. This was done in this paper here. And now there are a lot of works using neural networks, but most of them only consider one part of the system. Most of them are focusing on the dissipation because usually that's the hardest part to model from the physics. But what we are trying to do in this work is actually try to model everything from data. So we don't assume that we are given J or R or the Hamiltonian. Or also there's a lot of work in learning Hamiltonians, and this of course comes from the physics, from the people who work in physics. I'm also not mentioning other papers that maybe focused on one part of the structure, let's say. The last thing that you can do is transfer function measurements or using transfer function measurements, but this is a bit limited because you usually don't have access to those transfer function measurements in frequency domain. Okay, so in the work that I'm going to present and that we are still working on was inspired by physics-informed neural networks, where basically you have, on one side, you're basically trying to learn the dynamics, so you want to be as close as possible to the dynamics of the system, given some measurements or some data. And the other part is to enforce the physics and this is an example of a diffusion equation. And then all this is enforced by the laws. I'm not going to talk about PDEs. I'm just going to stay in finite dimensional systems. This was just a bit to illustrate what we are trying to do. And then you can write the loss function in terms of the physics parts, and then, at least in the PDE case, in the inverse problems, you can write it this way, but we can use something similar to enforce basically the structure, the physics part in our case. Okay, so let's consider first a very simple system. So consider that Q is actually identity. So we have x dot equals to j minus r x. So basically, the first method that we call here the direct method is to try to apply what I just mentioned about pins directly. So we have the dynamics part, so we trained the model to minimize the difference between the observed trajectories and those predicted by the model. And then we have the physics part, where we have a special structure for these J and R matrices. So J is Q-symmetric and R is symmetric positive definite. So how do we do this? So we have to take time as an additional input, as is usually done nowadays also with pins. And then we train the model for initial conditions that are the unit vector for each state, basically. So if we have a 2x2 system, it would be 1, 0, and 0, 1, basically. And then we take all those trajectories and then feed them to the neural network, basically. So that's our direct method. And then how do we test this? We test this with the Frobenius norm of the A matrix. So we reconstruct the A with the J minus R, and then we compare between our original one and the obtained one using the neural network. Okay, so take this very simple example. So it's very sparse, and then you can see that R is symmetric positive definite, J is Q-symmetric, and actually, without even looking at the eigenvalues of this matrix, I know that it is stable because of the structure of the system. Okay, so now we're trying to recover this J and R that result in this matrix A, and then I want you to remember this element here, -8, that we will use just to see what our results are. So we did several experiments with different measurement points and different architectures and so on, and then we obtained these results. So here we have 3 results. So one is for 80 measurements or observation points, 200 observation points, and 400 observation points. Remember that this element was -8 earlier. Now it's -4. That's very bad. And then we increase the data, and we see that it's getting closer, but still very, very far. And then we can see also in these plots. So here you can see the test cases for trajectories where we take as an initial condition where the first state is 1, basically. Then the second state is 1, third state is 1, and then fourth state is 1. Then you can see, for example, for this one, the results look quite okay. So basically, the dashed lines are the exact model, and then the solid lines are the estimated model. So here we are quite close, but also not that close. And then here it's like very bad. So what is wrong here? It looks like the neural network is trying to fit or gives more importance maybe to some initial conditions than others. So what we did is actually try to enforce it or force it to basically take all initial conditions. And now I will explain how we did that. So what we do is now we train all the initial conditions separately, and then we merge them together. So during each training session, we'll get some different J's and R's. And then the approximation of the trajectories will be these W's. So W of J is written in this way, where EI is the unit vector for the specific initial value, and then WR can be written this way. And then we put them all together in this big trajectory matrix PJ and this big trajectory matrix PR. And then our claim is that these matrices approximate the exponential J of T and exponential R of T. And now, basically, these are the general ones that can handle any initial value. And to see why this is true, consider the first state, or the state for the first initial value. It is exponential AT times E1, and E1 is the first initial value, and then this will basically take all the columns that are not the first one as 0, because it is 1 and all zeros. So basically it takes the first column of EAT. So, and basically we repeat that with all the initial values. How do we do this in practice? So we compute the eigenvalues of the approximation matrix that we obtain from the experiments. And then we also use the eigenvectors, and then we reconstruct, or we put everything together to reconstruct J and R. And then finally we can reconstruct A as J minus R. Now let's look at the results with this, what we call indirect method. We take 80 points now, we're getting a bit closer to the -8. Now if we take 200 observation points, then we are very close, and even closer if we take even more measurement points. And looking at the results here, of course they're much better than we had earlier, and basically we are able to track the trajectories that we were expecting. Just as a small comparison between the direct and indirect method, of course the indirect method will take much more time than the direct method. Don't look too much at the training time here. This plot is from a point where we didn't care too much about optimizing the code, and actually we didn't. So we did something better in the nonlinear case, but we didn't apply it on the linear case because we're more interested in the nonlinear case. But basically, this just shows us that we need basically more time for the indirect method, but we are able to have a lower error than the direct method. Okay, so that was it for the linear case. I should mention that there are other methods in the linear case that maybe even work as good or maybe better than what I showed you. But the real power of neural networks is to approximate nonlinearities, and then what we're interested in is to actually approximate nonlinear Port Hamiltonian systems. So here, consider again the nonlinear Port Hamiltonian system. For now, I don't consider inputs or outputs. I just consider this part. So we have J, R, and the Hamiltonian. And the architecture we proposed in the nonlinear case is in this way. So we have our data that will train a model that will train for a vector theta Q that will represent the Hamiltonian. Then we have another one that will represent the R, and then we have another one that represents the J. I will show you how we can get from these vectors to these matrices. So we use some parameterization. This helps us to reduce the number of parameters, because if you go to the nonlinear case with a high parameter as we did in the linear case, it's not really usable. I should also mention that in the linear case also we tested it for larger systems. So I showed you 4x4, but of course you can use it for larger systems. Okay. So basically, with these thetas, we can reconstruct our Port Hamiltonian system, and Okay, maybe, yeah, just 1 minute. Okay, maybe then let me start with the parameterization. So we actually parameterize the J, so we know that it is skew symmetric, so we can parameterize it with a vector to a strictly upper triangular matrix, and I will show this later, into this vector theta j. So if I have theta j, I can directly write the whole matrix. And basically, we do the same for Q and then for W. I'll just show you now in more details what we did. So here we have the J, as I said, in functions of theta j, W in terms of theta W, and then we just keep the upper left part of W to get R. And these VTU and VTSU are just taking a vector and put it in a upper triangular form, or in a strictly upper triangular form where the diagonal is 0, basically. And this is, I mean, you can see it also as a Cholesky decomposition, for example, for R, that helps us reduce the number of parameters. Okay, so now to the setup. So we generate training data by simulating multiple trajectories with random initial conditions. And then we take those initial conditions from a distribution. And then for each initial condition, we simulate the system over specific time horizon. And then we train the system, basically with the loss that we want our original or our obtained system that is close to the trajectories of the observed data. And then the other stuff is as usual. I will skip that, and then I'll go directly to the examples. So we have this simple mass spring system where the nonlinearity comes into the R, and H is actually quadratic, so as in the linear case. So we train our neural network for 10 seconds, and then we test it for 20 seconds. And here are different trajectories for different initial conditions. It's a bit difficult to see, so let me just select one initial condition and look at it in more details. So here, this big dashed line is the exact. The solid line is our method, and then the dashed line is the baseline. So a baseline is just a neural network where we don't enforce the structure, basically. And then we can see up to 10 seconds where we train the system. Most, all of them behave well. But after that, in the testing phase, you can see that actually the baseline model is starting to deviate, which our model doesn't because it learned the physics of the system. And these are other initial conditions where we notice the same thing. We can also do it for larger systems. So here we just take two coupled mass spring systems. It's easy to do in pH, so you just stack them, and then the resulting Hamiltonian is just the addition of the two Hamiltonians of the original systems, and then we do the same thing. So here we compare the position and then the momentum. And again, up to 10 seconds, it looks okay. And then after 10 seconds where we didn't train, you can see that the baseline model starts to deviate. Also here in the momentum case. Okay, I think I'm running out of time, so I'll just go back directly to the future work. So there's still a lot of ongoing work in this project. So we want to test combined nonlinearities because, for example, in the examples that we took, we only considered nonlinearities only either in J or R or the Hamiltonian. Now we want to basically combine all of them and try if it works. The other one is to include inputs and outputs. I've been saying that Port Hamiltonian systems are important because of the ports, but I didn't mention it here, but it's we already have some preliminary results, but it's still we're still working on it. Finally, to apply it for digital twins that I mentioned earlier, and there we will have to deal with noise and other problems from the measurements. And finally, these methods usually don't really work very well for really high dimensional systems, or it takes a long time. So we are thinking about learning embeddings or reduced order models directly from high dimensional measurements, for example, using autoencoders, but this is just still an idea at the moment. And with that, I would like to thank you for your attention.